Okay, Chapter 2, Section 2, Infinite Limits and Limits at Infinity. Okay, so let's begin by exploring this function. F of x equals to 1 over x minus 1. If you recall from algebra, we know that we can evaluate this function at various input values. So for example, we could figure out what is 1 over blank minus 1. We could figure out what happens when x equals to 2, for example. Put a little 2 there, put a little 2 there. And so we can conclude that f of 2 equals to 1 over 1, which is equal to 1, or that f of 2 equals to 1. Right? Or we can let x equal to negative 4, just arbitrarily picking a couple of values. F of blank equals to 1 over blank minus 1. And so if we let the input value be negative 4, that becomes negative 4. And so f of negative 4 equals to 1 over negative 5, or f of negative 4 equals to negative 1/5. Okay, so we can input values, and of course we know, hopefully by now, that we have to be careful not to divide by 0. So if someone goes, okay, well let's evaluate this when x equals to 1, then that means that f of blank equals to 1 over blank minus 1. And so that blank could be a 1, and that leads to 1 over 0. And we know we don't want to divide by 0, so we normally would say that's undefined. Right? This does not equal 0. It's a very common mistake. People see this and they go, oh, okay, the answer is 0. It's not 0, it's undefined. Right? Which means that this x equals to 1 is not in the domain of our function. So x equals to 1 is not in the domain of f of x. Okay, well, in algebra, we just kind of stopped there, and we didn't really do any further investigation. But now we want to examine this a little more. We don't want to just stop and go, oh, well, you can't plug in a 0 and it's undefined. We want to investigate it a little more. And so what we're going to do is we're going to plug in values that are not equal to positive 1, but are close to positive 1. To do that, we're going to go back to our calculator. We're going to put this back into our calculator and then use the table feature in our calculator to plug in values that are close to 1 from either side and see what happens as we do that. So from our calculator, quit, go to y equals, clear, and then type this in. So I'm going to do 1 divided by, and then make sure I put parentheses to make sure all of it is in the denominator. And it's going to be x minus 1, close parentheses, enter. Okay, so now that equation is there. It's under y sub 1. I'm going to go back to table set. So second table set, make sure that that's a 0 and a 1. Well, actually, that doesn't really matter. What's important is that this is under ask and this is under auto. Use your arrows to go down and change them if you need to. You can hit enter to change it. Good. Okay, so we want to go to table. So second table. And then delete all the previous values on there. That was for a different equation. Okay, we're interested in seeing what happens as we get closer and closer to 1 from either side, as we approach 1 from either direction on the number line. So let's begin from the right-hand side. So as I start out with values that are definitely larger than 1, like let's say, for example, a 2. For example, a 2. Well, 2 we already saw when we did it by hand. That 2 leads to 1. Right, that's what this calculator is doing. It evaluates it. You plug in that number and it'll crunch this out and it'll give you that value right there. On the other hand, we had already evaluated a negative 4. So if we plug in a negative 4, the calculator will automatically give me a negative 0.2, which is what this is. When we convert negative 1 divided by 5, we're going to get a negative 0.2. Okay, so back to our attempt to figure out what happens as we get close to 1, right? We can't plug in a 1. If we evaluate it at 1, we're going to get an undefined, but we can get close to it. So let's start with 4. Oops. 3, 2. So I'm like walking toward 1. Maybe 1.9, 1.8, 1.6, 1.4, right? And the actual values I pick are a little arbitrary. I'm just walking closer and closer and closer to 1. We'll see when we get our graph what these values translate to. 1.4, 1.2, 1.1, 1.01, 1.001, right? And so see what's happening here. When we started at the input value of 4, we got that decimal, 0.3333. When we let x equal to 3, we got a 0.5. When we let x equal to 2, we got a 1. And then as we got closer and closer to 1, but always approaching it from the right-hand side, we see that the output values begin to grow out of control. Okay? The closer we get to 1, the larger these values are going to get as we approach from one direction. Okay? Now, the other side, let's say we want to approach 1 from the other side. Let's say we start off at -3, then -2, then -1, then 0, then 0.1, then 0.2, then 0.4, then 0.6, then 0.8, then 0.9, then 0.999. We see that the output values begin to grow toward negative infinity. They're getting infinitely large in the negative direction. Let's see what this looks like on Desmos. Okay, here we are. I typed in 1 over 1 minus x right in here, created a table on Desmos. So what this is going to do is give me an input-output relationship and ordered pairs that will then graph over here. So for example, if I plug in a 5, I'll end up putting a 5 right in here. So it'll be 1 divided by 5 minus 1. 5 minus 1 is 4, so it ends up being 1/4. 1/4 is exactly to 0.25. Okay, and then we get this ordered pair right in there, 5 comma 0.25. Okay, so then we want to walk toward 1, right? We want to get closer and closer to 1. So now if we put in a 4, we get this ordered pair, 4 comma 0.333333. And then we want to get closer to 1, so then maybe a 3 leads me to this value, 3 comma 1/2. So if we put a 3 in here, 1 over 3 minus 1, 3 minus 1 is 2, so 1 over 2 is a half, 0.5. Okay, then we want to get closer to 1, so put a 1 there, a 2 there. So put a 2 there, we get 1 over 2 minus 1, which is going to be 1 over 1, which gives you a 1. Again, remember, if we put a 1 there, we get a error, right, an undefined. 1 over 1 minus 1 is 1 over 0, it's undefined. So we don't want to do that. But we want to get close to 1. So how about 1.9? 1.9 will lead to 1.11. That's going to be this little dot right over there. About 1.8. About 1.7. About 1.6. About 1.5. And we can start to see what's happening as the input values get closer and closer to +1, but always from the right-hand side, the output values are starting to get larger and larger and larger. Oops, 1.4, 1.3, 1.2, 1.1, about really close, 1.01. Ooh, at that point, 1.01, the output is 100. That's already outside the scale of this guy, so I'd have to zoom out to find it. There it is, way up there. So it grew quite a lot. From 10, it just jumped to 100. And if I get even closer, 1.001, jumps to 1,000. So I'd have to zoom out again to find the value way up there, right? So this confirms that as the input values get closer and closer and closer to 1, but always from the right-hand side, the output values are going to be getting larger and larger and larger and larger. Okay, so what happens when we approach it from the other direction? Okay, so let's center this back over here. Now let's approach 1, but from the other direction. So let's begin at negative 5. I get this little guy here. Negative 5 leads to negative 0.167. So if we put a negative 5 into here, we end up with 1 over negative 5 minus 1, which becomes 1 over negative 6. 1 divided by 6 is 0.167. So we get that, and it stays as a negative. And again, we're walking toward 1, so we want to get closer. How about negative 4? That leads to negative 0.2. About negative 3 leads to negative 0.25. About negative 2. About negative 1. About 0. Remember, you're allowed to plug in a 0. It's not that the 0 is in the domain of the function. You're allowed to plug in a 0. When we plug in a 0, we get 1 over 0 minus 1, which is just going to be negative 1. Okay, so that leads to this point right over there. And let's keep going. How about 0.1? How about 0.2? 0.3, 0.4, right? As I'm slowly getting closer and closer and closer to 1, but always approaching from the left-hand side of 1, I see that my output values are getting larger and larger toward the negative direction. 0.5, 0.7, 0.8, 0.9. At 0.9, the output is negative 10, so I already have to kind of move this a little bit so we can see it. There it is. When I input a 0.9, the output is negative 0.10. And so we see that if I get even closer, 0.99, the output is going to be negative 100. I'm going to have to zoom out and go down here in the negatives to find it. There it is, way down there. 0.99 comma negative 100, and so we know that if we go even closer, 0.999, 3 nines, jumps to 1,000, and then we can just keep going from there. Okay, so I graphed individual values of using this table, but now if I just come back and graph the entire function, right, if I let the calculator graph an infinite number of ordered pairs, all of them, we see something that looks like this. This curvature here, so let me get rid of the individual points. That graph in blue is the graph of f of x equal to 1 over x minus 1, right? So this blue is like an infinite number of ordered pairs, all possible values of the input, and we see what happens to our graph. So right around 1, we have this behavior. Right around 1, the input values, as the input values approach 1, let me zoom in actually. As the input values approach 1 from the right-hand side, the output values begin to grow, and they grow out of control toward positive infinity. As the input values are growing toward 1, we see that the output values begin to grow out of control toward negative infinity. So we say that this kind of behavior has a vertical asymptote at 1. So you'll see these in graphs. Remember that this red part is not part of the original graph. It's just a vertical asymptote to help us identify that there's 1 there, right? And that's the behavior that happens around this. Okay, so once we finished investigating this function with our calculator using the table function, to investigate what happens around the input value of 1, or a graphing technology like Desmos. Now we're ready to express what happened in using notation, calculus notation. So this is how we would express that. We want to say that the limit as the input values approached 1 from the right-hand side of this function, 1 over x minus 1, equal to positive infinity. And we also want to say that the limit as x approaches 1, but from the left-hand side. Remember, this does not mean it's -1. It means that we're approaching the number 1, but from the left-hand side. So all the input values are a little bit smaller than 1. Of this function, 1 over x minus 1, and these were equal to -infinity. Okay, so this is one way to express it. Another way to express it would be to say that f of x approaches to infinity as x approaches to 1 from the right-hand side. That would be that one. Or we can say f of x approaches to -infinity as x approaches to 1 from the left-hand side. Right? That would be another way of saying this one. Either one is fine, but this one is the one that's most popular, though some people really like expressing it this way. Note that I've put a restriction here. We know that it goes toward infinity as long as x approaches to 1 from the right-hand side, and we know that this function approaches -infinity as x approaches to 1 from the left-hand side. But then if we have an unrestricted limit, if we just say, well, what happens as x approaches to 1, and don't put any conditions on the direction, then we would say that, combining those two things, the limit as x approaches to 1, no restrictions, of 1 over x minus 1, well, does not exist. Right? I can't say positive or negative infinity because it depends. Which value of x did you choose? We know that if they're above 1, close to 1, but a little bit above 1, then we're going to get a very large positive number. If we choose an input value that is close to 1, but a little bit below 1, we're going to get a very large negative number. So we can't even really describe anything, so we just say that it does not exist. Okay? To be clear, all of these do not exist. The limit does not exist in any of these cases. Let me write that down. So the limit does not exist. Limit does not exist. And also here, the limit does not exist. Right? The limit exists only in cases where this turns out to be some constant. Right? If it turns out that as I get really, really close to this value, this whole thing begins to get infinitely close to some constant, that's when the limit exists. This is a case where it's growing out of control, so it does not go toward a specific number. So the limit does not exist, but it doesn't exist in a very special kind of way. It doesn't exist, it fails to exist in this way. It grows without control toward positive infinity. And this one does not exist, but in a special way, it grows toward negative infinity. Right? It's kind of like if somebody asks you, did you successfully complete your calculus class? And you say, I withdrew. Okay, well, that's no, you did not successfully complete your class, but you did it in a special kind of way. It's the kind of way in which you withdraw before you get a letter grade that's still failing to successfully complete your calculus course, right? Okay, so in some cases we can add a little bit more information than just simply say it does not exist. We can say it does not exist in a special kind of way. It does not exist in that it grows toward positive infinity, or it does not exist in that it grows toward negative infinity. And well, in this case, if we don't even restrict the domain, the input values, if we make this the unrestricted limit, well, then it just doesn't exist. We don't even have any special information to add to it. Here is what your textbook provided. So similar to what I did with Desmos, we have a table where we have input values of x as they get closer and closer and closer and closer to 1, but always from the right-hand side. Right, so here's our function, and then you see these outputs. Right, so again, confirming what I just did, the output values are getting larger and larger and larger and larger. Right, and then in the other direction, as x gets closer and closer to 1, but always approaching from the left-hand side, we see that the output values are getting to be larger negatives, larger negatives, larger negatives. And so that, again, agrees with our graph that we got from Desmos, right? It looks like this. As we walk toward 1, as the values of x selected for the input, we choose a value there, 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 right? This is the number 1 right in here. As we get closer and closer and closer to 1, but from the right-hand side, we see that the output values are growing out of control. F of x is growing toward positive infinity, right? Growing toward infinity. On the other hand, as we choose values of x that are approaching 1 from the left-hand side, so maybe we choose an x value there, and then we choose 1 there, and then we choose 1 there, and we choose 1 there, and we choose 1 there, and we get closer and closer and closer to 1 from the other direction, the output values are going to be growing toward negative infinity. They get larger and larger and larger and larger toward negative infinity. They grow that way. They grow toward negative infinity. And that's what this table confirms. Okay, so at this point, the only way we can analyze this is by using a table on our calculators so that we can confirm what happens near that value, or by graphing it and being able to judge from the graph that we have a vertical asymptote, right? This dashed line here is not part of our actual function, but it helps structure what's happening with our function. It lets us know what's the behavior of what's happening to our function near that value of the line x equals to 1, right? This vertical line here is the line x equals to 1. Okay, so if we let f of x equal to 1 over x minus 1, the function is discontinuous at 1. We already saw that. F of 1 does not exist. As x approaches to 1 from the right-hand side, the value of f of x are positive and becoming increasingly large. We say that f of x increases without bound. And we write that, we express that using this notation, right? So it's important to pay attention to the details here. We have the limit, LIM, the limit, as the input value x approaches to 1 from the right-hand side. That's what that little plus symbol here indicates. This little plus guy right there indicates that we're approaching 1 from the right-hand side of 1 over x minus 1, where this is the function f of x. So often we'll see this replaced by f of x instead of writing down the actual equation, equals to infinity. Or another way of describing this is to say f of x, which is equal to 1 over x minus 1, approaches infinity as x approaches to 1 from the right-hand side. Again, notice that simply saying infinity gives us some information of what's happening to our function. It lets us know that the output is growing out of control, growing without bound toward infinity, but that does not mean that the limit is infinity, right? This means that the limit does not exist. It just doesn't exist in a very special kind of way. As x approaches to 1 from the left-hand side value of f of x, the output values are negative and becoming increasingly large in a negative direction. So we say that f of x decreases through negative values without bound. And we write it this way. So the limit as x approaches to 1 from the left-hand side of 1 over x minus 1 equals to negative infinity, or that f of x equals to 1 over x minus 1 approaches negative infinity as x approaches 1 from the left-hand side. Okay, again, negative infinity is not a real number. It does not. It still means that this limit does not exist, right? If the simple question was, does this limit exist, yes or no? The answer is no, it does not exist. But if you want more information, in this case, we can say it does not exist, and it doesn't exist in a special kind of way. It doesn't exist because it grows without bound toward negative infinity. Okay, so the infinity symbol is used to describe the manner in which limits fail to exist. Such limits are called infinite limits. The symbol infinity is used to describe the positive growth without bound, and the symbol negative infinity is used to describe negative growth without bound. Okay, so infinite limits and vertical asymptotes. The vertical line x equals to a is a vertical asymptote for a graph of f of x if f of x grows toward infinity or f of x grows toward negative infinity as x grows toward a from the right-hand side or as x grows toward a from the left-hand side. Right? So it's what we've been describing. As the input values get closer and closer to a, from one side or the other side, the output values would either grow toward positive infinity or down toward negative infinity. Locating vertical asymptotes. So if f is a polynomial function, then the limit as x approaches to a of f of x equals to f of a. That's a special property of polynomial functions. Okay, so if we are working with a polynomial function, then the limit as x approaches to a of f of x equals to f of a. So polynomial functions have no vertical asymptotes. That's what this is saying. A vertical asymptote of a rational function can occur only at a zero of its denominator. Remember, a rational function is a function that looks like a giant fraction where the numerator is going to be a polynomial and the denominator is going to be a polynomial. So a vertical asymptote can only happen when we have the possibility of having a zero in the denominator. Okay, theorem 1, locating vertical asymptotes of rational functions. So if f of x is given to be a rational function where the numerator is n of x divided by d of x, so n of x here represents some polynomial function in x, d of x represents another polynomial function in variable x. So together they create this fraction where the numerator is a polynomial, the denominator is a polynomial. That makes it a rational function. And if we have knowledge that at x equals to c, d of c equals to 0, and n of c does not equal to 0, then the line x equals to c is a vertical asymptote of the function f. What in the world does that mean? Okay, so if we have some polynomial function, say this one here. So here, for example, this is representing that, for example, n of x. We could think of that as x squared plus x minus 2. And the d of x, that's another polynomial function in x, so maybe it's the x squared minus 1. This is a polynomial, this is a polynomial, right? This is a polynomial. This is a polynomial. Together, if we divide them, we have a rational function. Okay, so where is there a vertical asymptote? A vertical asymptote will occur whenever the denominator is equal to 0 and at the same time the numerator does not equal to 0. So the first thing we want to do is figure out when does the denominator equal to 0. To do that, we're going to factor this. So if we factor it, we see that f of x equals to, well, the denominator, that's going to be difference of squares. X squared minus 1, that's just going to be x plus 1, x minus 1. And then x squared plus x minus 2. Two numbers are multiplied to negative 2, but add to positive 1. That's going to be x plus 2, x minus 1. Good. So that's how that one factors. So if I factor this, then I'll end up with x squared, x plus 2, x minus 1 in the numerator, and then x plus 1, and then x minus 1 in the denominator. So from this information, I can see that if I let x equal to, if x equals to positive 1, then what are we going to get? We're going to 1 there, a 1 there, a 1 there, a 1 there. We're going to get a 0 in the denominator, right? The denominator is going to be blank plus 1, blank minus 1. So if we let x equal to 1, positive 1, I'll get a 1 there and a 1 there, which means I'll end up with a 2 times 0, which means I'll get a 0. So when x equals to positive 1, I'm going to get a 0 in the denominator, right? That's what this is saying. The denominator, d of c, equals to 0. And at the same time, when I plug in 1 in the numerator, oh, well, I'll get a 0 in the numerator as well. But we'll look at that in a second. Okay, so now what about at negative 1? When x equals to negative 1, what happens then? Well, it is going to be blank plus 1, blank minus 1. So if I let that blank be a -1, -1, and -1, I'll end up with 0 from here, so it'll equal to 0 times -2, so the whole thing will be 0. Okay, so I can tell that the denominator will be 0 at two different values. One of them is going to be at x equals to 1, and the other one is going to be at x equals to -1. Let's investigate -1 first, and then we'll come back and investigate x equals to 1 second. So if we want to investigate what's happening here, let's look at this function near that by using our calculator and plugging values close to -1. So we want to create a table of values where we have inputs and we have our f of x squared plus x minus 2 divided by x squared minus 1. And we want to start plugging in values that are close to -1. So let's go to our calculator. Y equals parentheses x to the power of 2 plus x minus 2 close parentheses divided by close parentheses x to the power of 3, sorry, x to the power of 2 minus 1, minus 1, close parentheses. So x squared plus x minus 2 divided by x squared minus 1. Good. So here's my function. I'm going to go over to table, delete old values, and we want to explore what happens as x approaches to -1. So as x approaches -1, let's start off by going from -3 to -2 to -1.9, -1.8, -1.6, -1.6, -1.4, -1.2, -1.01, -1.001, -1.00001. Look, it's growing toward -infinity. Good. So as I approach -1 from the left-hand side, this is growing toward -infinity. Okay. What about the other direction? What if I approach -1 from the other direction? Then let's start off at 4 and walk our way down toward -1. Well, let's start off at 0. It's too far away. 0, then -0.1, then -0.2, then -0.3, then -0.4, then -0.5, then -0.6, then -0.7, then -0.8, then -0.9, then -0.99, then -0.999, 3 nines, then -0.999999, getting really large, right? I can use my arrows here to highlight it and see it's a much larger value. Okay, so as the value gets closer and closer, the input values get closer and closer to -1, but always from the right-hand side, this is growing out of control toward positive infinity. Okay, so based on that, I feel comfortable indicating that the limit, you know what, we don't need this. The limit as x approaches to -1 of my function f of x is going to be equal to negative infinity as long as I approach it from the from the left-hand side, and the limit as x approaches to negative 1 from the right-hand side of f of x. Okay, so we're going to have a vertical asymptote at x, vertical asymptote at x equals to negative 1. Good. Okay, what about at positive 1? What's happening there? So again, let's use our calculator to input values near the neighborhood around positive 1. What happens as the input values approach 1 from the right-hand side, from the left-hand side? What's happening to this equation? Okay, so we're going to go back to our table. We already have the equation there, so we don't have to rewrite it. Let's go back to our table. Up, 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 up. So we're trying to get close to positive 1. So starting at 3, 2, 1.5, 1.4, 1.2, 1.1, 1.01, 1.001, 1.00001. Okay, so look at the behavior that's happening here. As I approach 1 from the right-hand side, the output values are not growing out of control. They seem to be converging towards something. They're getting closer and closer and closer and closer to 1.5. There it rounded it to 1.5, but if I use my arrows to highlight that little box, I can see that it's actually 1.4999975000125. So we can see that it's really, really close to 1.5. It seems to be heading that way. It's heading toward 1.5. Okay, what about if we approached 1 from the other direction? So let's say that we start off at 0, and then we do 0.1, then 0.2, then 0.3, then 0.4, then 0.5, then 0.6, then 0.7, then 0.8, then 0.9, then 0.99, then 0.9999. Well, okay, so we can see that the same thing is happening. As I approach 1 from the other side, the output values are also getting closer and closer and closer and closer to 1.5. So from both directions, they're approaching 1.5. So based on this work, I feel confident in coming back over here and saying that, space here, the limit as x approaches to 1 from the left-hand side of this function is equal to 1.5. The limit as x approaches to 1 from the right-hand side of f of x equals to 1.5. And so because both limits exist from both sides, from the left-hand limit and the right-hand limit both exist, and they both equal the same thing, I could just say the unrestricted limit exists. The limit as x approaches to 1, no restrictions, left or right, of f of x is just going to be equal to 1.5. Okay, once again, let's explore this with Desmos. So I typed in our equation into here, and remember, we want to explore what happens to our outputs as the inputs get closer and closer to negative 1. That's one consideration from both directions. And the other one is what happens to this function as we get closer and closer to positive 1, both directions. And we care about 1 and negative 1 because those are the values that will result in an undefined, right? If we try plugging in 1, we're getting undefined. If we try plugging in a negative 1, we're going to get an undefined from this equation. So those are the ones that are interesting values to explore. Okay, so let's begin with the negative 1. If we approach from this side, approaching toward negative 1, approaching from the left-hand side, say we try plugging in negative 3. Okay, -3, if we plug it into here, the computer automatically determines that that's going to give you a 0.5, so it gives you this ordered pair for the function, -3 comma 0.5. Then we keep going. How about -2? Oops, -2. -2 leads to a 0. Okay, and then how about -1.9? How about -1.6? How about -1.4? About -1.2? Okay, so we can see where this is going. Let's zoom out a little bit. We can see that this seems to be heading in that direction. We plug in just a couple more values just to confirm. -1.1. Okay, there it is. So it seems to be the case that as the input values get closer to -1 from the left-hand side, the output values are going to be growing toward -infinity. And then let's confirm the other direction. What if we approach -1 from the right-hand side? As we approach it from the right-hand side, then let's change the color of these guys. Red? Not too aggressive. Blue. Okay. So as we approach from the other direction, let's say we start off at 0. 0 is okay. We plug in a 0, we're going to get a 2. In fact, let's start off with a little farther. How about 0.5? 0.2? 0.1? How about just 0? Then -0.1. -0.2. -0.4. -0.7. Right? So we start to see that it's starting to grow that way. About -0.9. And we get an 11. That's already out of bounds here. I got to zoom out. Here it is. -0.9 leads to an 11. And then if we get even closer, -0.99, well, that already leads to 101. It's already growing way out of control here. I'd have to zoom out a lot to find it way up there, -0.9, comma 0.11. Okay, so I think that confirms our suspicion from before, the same results that we got from our calculator. As the input values approach -1 from this direction, we start to see that the graph will grow toward positive infinity. As the input values grow toward -1 from the left-hand side, we see that the values grow down toward -infinity. So now if I just graph the function, meaning that the calculator or the program here is going to graph all possible inputs and get all possible outputs, then the graph would look like that, right? That smooth-looking curvature is really just an infinite number of ordered pairs, where we have just happened to find a few of them. But again, we see that the behavior is consistent. And so what we have found here is a vertical asymptote at x equals to -1. So it looks like that, right? So the red one is not part of my graph. It just helps structure what's happening. Okay, the other interesting one was what happens around x equals to +1. So let's go back to our table here and again plug in values close to +1. So let me walk toward +1 from this direction. So 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.99, 0.999. So we can see from the values over here that as we get closer and closer and closer and closer to 1 from the left-hand side, the output values just seem to be going toward this value there, just seem to be going toward 1.5. Now if I just plug in 1, I'm going to get an undefined. So this is a little misleading. It almost makes you feel like it's a smooth, continuous graph there, where in fact there's a little hole. There's a little hole there at 1. At input 1, output 1.5. Okay, but if we approach 1 from the other direction, you'll see that exactly the same thing happens. So if we approach 1 from the other direction at 1, then, I'm sorry, at 2, then 1.9, and then 1.8, and then 1.7, and then 1.6, and then 1.5, and then 1.3, and then 1.2, and then 1.1, and then 1.01, and then 1.001. Again, we see that as we walk toward 1 in the other direction, it starts to go toward the value of 1.5. Okay, so it confirms the results we got from our calculator. So this is what your author provided for you in your textbook. We see that your author provided you with a table similar to what we've been creating, where we have our function and we have input values. The input values are growing toward or heading toward -1 from the left-hand side, as input values are selected from the left-hand side of -1. Closer and closer to -1, we see that the output values begin to grow out of control toward the -infinity direction, right? As input values are selected, that one, getting closer and closer and closer, and walking toward -1, but from the left-hand side, we see that the output values are heading toward -infinity. And as the input values are selected here and here and here and here and here and here and here, as x approaches -1 from the right-hand side, we see that the output values are growing toward, heading toward +infinity. Good. Okay, and then around +1, something different happens. As x approaches to 1 from either direction, as the input values get closer and closer to 1 from either direction, we see that the output values just begin to get closer and closer and closer and closer to this value right there, which is the value 1.5. So the limit as x approaches to 1 of f of x is going to be equal to 1.5. Okay, one more thing we can get out of this is note that if we plug in a value of -1 to this function, the original function, so we have f of blank equals to blank squared plus blank minus 2 divided by blank squared minus 1. And so let's let x equal to -1. Put a -1 there, a -1 there, a -1 there, and a -1 there. Okay, so -1 squared, that's going to be +1. +1 minus 1 is just going to become 0, minus 2. So this becomes -2 divided by 0. Okay, when we have a case such as this, where the denominator is 0 and the numerator is not 0, that's when we're going to get a vertical asymptote. Note that when we plug in +1, we end up with the following: f of blank equal to blank squared plus blank minus 2 divided by blank squared minus 1, and we let x equal to +1. We put a 1 there, put a 1 there, put a 1 there, put a 1 there. We end up with 1 squared plus 1 minus 2. That's going to be 0. We end up with 0 divided by 0. 0 divided by 0. This is what we call undeterminate. This is indeterminate. So when you run into a rational function, the first thing you should do is factor it, figure out when are we going to get a 0 in the denominator. When you find those values, then come back and plug it into your function. If it turns out that we end up with something that's not 0 divided by a 0, we're going to get a vertical function, a vertical asymptote at that value of the input. So vertical asymptote at x equals to -1, just like we did here, right? This vertical asymptote is x equals to -1. On the other hand, if we get something where we end up with a 0 divided by a 0, that rule does not apply. We have to do more work. One of the things we could do is go back to our tables and figure out the behavior around 1, just like we already did. And as we saw from our work with our calculator, this converges to 1.5 from both directions. But how can we get that from here, from the work? So what we want to do is that when we get an indeterminate form like this, you can either use your calculator and use the table form to figure out what's happening as the input values get closer and closer to 1, or we could do the following in this case, factor. Okay, so now when we want to think about the limit as x approaches to 1 for this, the case where we had the indeterminate form, let's write it out this way. The limit as x approaches to 1, positive 1, it's an unrestricted limit, so we're not designated from one direction or the other, of my function x squared plus x minus 2 divided by x squared minus 1. This is going to be equal to the limit as x approaches to 1 of, okay, and then what we could do is factor this. We already had factored it. This is x plus 2, x minus 1. And the denominator is x plus 1, x minus 1. Okay, so then the question, I think, is going to be, well, can we cancel these? And the answer is yes, you can, because of this. It's a very subtle thing you have to catch. This is saying we're only considering input values that are close to positive 1, but are definitely never going to be equal to 1, right? We don't care what happens to 1. We know what happens to 1. If we put a 1 here, we're going to end up dividing by 0. So this right here, this is saying, I promise I'm not going to consider x equals to 1. I'm going to get really close to 1, but never exactly 1. It might be 0.9 or 0.999 or 1.001, anything like that. So if we choose any number that's close to 1 but never 1, then this over this ends up being the same number, so we can cancel them, right? So for example, if I let x equal to 0.9, then just this part of it would be 0.9 over 0.9. Well, then those guys can cancel, right? Or if I let x equal to 1.001, then this over this would be 1.001 divided by 1.001. A very small number divided by an identical very small number. These guys can cancel, right? The only time we have a problem is when this is 0. 0 minus 1, excuse me, when the input value is 1, because then we'd end up with 1 minus 1, which is 0, divided by 0. That's not something we can deal with, right? Okay, so because we are dealing with the limit, we're promising we're never going to consider the case where x equals to 1, then we can just cancel those. And what we're left with is the limit of this, which is equal to the limit as x approaches to 1 of x plus 2 over x plus 1. So now we can just evaluate this and say that this is equal to the limit of 1 plus 2 over 1 plus 1, which gives me 3 over 2, which equals to 1.5. So you see that this is the algebraic way of getting the same answer we got from using the table form on our calculator. All right, let's consider one more example. Let's say f of x equals to this rational function, x squared plus 20 in the numerator, 5 times x minus 2 squared in the denominator. Okay, so the first thing I want to note is that this is a rational function, and so I care about when the denominator is going to be equal to 0. So let's set the denominator 5x minus 2 squared over off to the side. And if I want to figure out when does that equal to 0, then a little bit of algebra lets you conclude that it must be the case that this is going to happen when x equals to 2. At x equals to 2, we get 2 minus 2 squared. That's going to be 0 squared times 5 is equal to 0. And note that if I evaluate this this rational function at 2, f of blank equals to blank squared plus 20 divided by 5 times blank minus 2 squared, and I evaluate it at 2, well, obviously we're going to get a 0 in the denominator, and in the numerator we'll end up getting 24, right? So this is again the case where we have a non-zero divided by 0. So just from that, I can already conclude that there will be a vertical asymptote at x equals to 2. At x equals to 2. So I have the vertical asymptote. Now I just have to determine what happens to my function as the input values approach 2 from either side. There's only a couple of options. The function can approach positive infinity, or it can approach negative infinity from either side. So in order to figure out which is which, we really don't have any other choice but to use our calculator and use our table to come up with those values, or some other technology like Desmos. So I'm just going to use Desmos this time. Okay, so on Desmos, I typed in my function here. It's going to be a rational function where the numerator is x squared plus 20. The denominator is 5 times x minus 2 squared. And I also create a little table here. So now I'm interested in the behavior around x equals to positive 2. Although I already know that there will be a vertical asymptote there, right? I just want to know if my function will approach positive infinity in this direction, or maybe positive infinity in this direction, or negative infinity in this direction, or negative infinity in this direction. So I already have some amount of information, and I can just use a few values in order to confirm that and see where it's heading. So let's approach 2 from the left-hand side first. So how about 0, then 1, then 1.1, then 1.4, then 1.5, then... Okay, so they're already getting pretty large. So it looks like it's heading that way. Right? Maybe a couple more to confirm it. 1.7, 1.9, 450. Okay, so they're growing out of control. My graph is just out of scale here. But I can see in my table values that they are getting very, very large. Good. Okay, so then I can approach 2 from the other direction. So how about I start at 4? How about 3? About 2.9? About 2.6? And again, we see that they are growing toward positive infinity. 2.4, 2.2, 2.1, 2.01, 0.1. So we can see that they are heading toward positive infinity in both directions. And if I just graph the whole function, it looks like that. Okay, so the limit as x approaches to 2 from the right-hand side grows toward positive infinity. The limit as x approaches to 2 from the left-hand side grows toward positive infinity. Right? So it doesn't exist on either side, but it doesn't exist in a very specific way. So let's write that down. So we would conclude all of this by saying there's a vertical asymptote at x equals to 2. Okay, so the limit as x approaches to 2 from the left-hand side, my function, approaches positive infinity. The limit as x approaches to 2 from the right-hand side of our function approaches to infinity. In this case, they both agree. They both are heading toward positive infinity. So I can say a slightly stronger statement and say that the unrestricted limit, the limit as x approaches to 2 from either direction, is going to be positive infinity. And remember that if the question was, does the limit exist? The answer is no, the limit does not exist, right? This means does not exist. The limit does not exist. The limit does not exist. Infinity is not an answer. It's a direction. It's a concept. It's additional information on how it fails to exist, but it does not mean that it exists. Okay. Okay, so these are the two examples we've looked at so far. We had this example with this function, and we approached the limit as x approaches -1 from the right-hand side, the limit as x approaches -1 from the left-hand side. And in this case, we saw that the function was growing toward positive infinity. In this case, we saw that the function was growing toward negative infinity. Because they don't even match, then the unrestricted limit does not exist. We really can't say anything about it. On the other hand, we had this other equation, and we saw that the limit as x approaches positive 2 from the right-hand side was growing toward positive infinity. And the limit as x approaches 2 from the left-hand side is also positive infinity. Therefore, they at least can match and say that the unrestricted limit of that equals to infinity. But remember, that also means that it does not exist. It just doesn't exist, but we have some more information. Okay, moving on. Limits at infinity. Limits at infinity and horizontal asymptotes are used to describe the behavior of functions as x assumes arbitrarily large positive values or arbitrarily large negative values, right? In other words, now we're looking at the input values of our function. We're not going to get arbitrarily close to some constant value on the x-axis like we've been doing so far. Now we're going to consider what happens as we let the input values grow out of control toward either the positive infinity direction or the negative infinity direction, right? So the symbol infinity, this little symbol here, is used to indicate that the independent variable is increasing without bound toward the positive direction, and minus infinity is used to indicate that the independent variable is growing without bound toward the negative direction. Limits at infinity are limits where either x grows toward positive infinity or x grows toward negative infinity. So let's compare these two functions. We have f of x equals to x cubed, and we have g of x equals to 1 over x to the third power. Okay, using Desmos, I can graph both of them. This is f of x equals to x to the power of 3. That's this red one here, right? That's what the graph looks like. And then I have g of x equals to 1 over x cubed, and that would be this blue one here. Okay, so what we care about is what happens as the input values grow toward infinity in positive direction or toward infinity in the other direction. So let's first of all consider in this direction. Notice that as the input values grow larger and larger and larger and larger, x cubed is going to grow larger and larger and larger and larger. So it's going to grow toward infinity. On the other hand, as the input values of x grow toward positive infinity, the output values are going to get closer and closer and closer and closer to 0. That's what we want to get out of this. And likewise in the other direction, as the input values, the x values grow toward negative infinity, the x cubed values will grow down toward negative infinity. And as the input values grow toward negative infinity, the output values of the g of x function will grow toward 0. Okay, so we had f of x equals to x cubed, and we had g of x equals to 1 over x cubed. So that would be this one. This blue one is g of x, also this one. And then the red one is the f of x. Okay, and so what we want to point out that as the input values, as the x's are chosen, like let's say we let that be x, the first x, and then the second one, and the second one, right? As this grows toward infinity, positive infinity, the output values of the f of x function grow out of control. They grow toward infinity. Good. So we want to say that f of x will grow toward infinity as x grows toward infinity. As the input values grow toward infinity, f of x will also grow toward infinity. What about the other direction? As x is chosen to be values that grow this way toward negative infinity, then the x cubed function values also grow toward negative infinity. So f of x will grow toward negative infinity as x grows toward negative infinity. That's the pattern I see with this red one. Good. On the other hand, look what happens with the blue one. as the input values grow toward infinity, as I put in larger and larger and larger values, this will get closer and closer and closer and closer to 0. Right? The outputs converge towards 0. They get infinitely close to 0. So I would express that by saying that g of x will grow towards 0 as x grows toward infinity. And the same thing happens in the other direction. As I let the input values get larger and larger and larger and larger, the output values are going to get closer and closer and closer to 0. So g of x will also grow towards 0 as x approaches negative infinity. Okay, so that is a pattern that we want to learn from and just make a general statement about functions that fit a certain pattern. And that's what this next statement is about. So, theorem 2, the limits of power functions at infinity. So if p is a positive real number and k is any real number except 0, then it's true that the limit as x approaches negative infinity of k over x to the power of p will be 0. And the limit as x approaches to infinity of k over x to the p power will be 0. This is similar to what we just saw, right? So examples 1 and 2 are very similar to the case we just looked at where we had 1 over x cubed. So we were looking at the limit as x approaches, say, infinity of 1 over x cubed. And we saw that as the input values grow toward positive infinity, this whole thing grew toward 0. This is an example of this. This is where k is being represented. This is where k equals to 1. So this is saying, oh, and p equals to a 3. P equals to a 3. And that would be this case right here. So it says, if p is a positive number and k is any real number, this will be true. So anything that fits that form, where this is a positive real number and k is any number at all, then this thing will converge towards 0. So if we were looking at another similar one that said, for example, the limit as x approaches to infinity of 7 over x to the power of 9, then I already know that this is going to be 0. Right? Here, this would be the case where k equals to 7 and p equals to 9. It doesn't even have to be a counting number. It could also be like a decimal. The limit as x approaches to infinity of 2.7, say negative 2.7, divided by x to the power of 3.2. It's a little uglier, but it fits this form. Here, the p is this. P equals to 3.2. And k equals to negative 2.7. So I know that the whole thing is going to converge towards 0. Good? Okay, so that's what this one is saying. The limit as x approaches to positive infinity, right? As the input values get uncontrollably large, as we input values that are getting larger and larger and larger toward the positive direction, positive infinity direction, then this whole thing will get infinitely close to 0 as long as these conditions are satisfied. K could be any real number, positive, negative, decimal, doesn't matter, but p has to be a positive number. If we let p be a negative number, then we know that that means that we can simplify this by moving the x to the positive p power up to the numerator, and then that causes problems, right? So we're going to make sure that it's positive. On the other hand, if we have the exact same scenario, so all of these, but now we're plugging in values that are going toward negative infinity, same thing happens. It doesn't matter whether the input values are very large positive or very large negative. If we're dealing with something that fits this form, we know that it's going to grow towards 0, right? Notice that in both cases, the numerator stays still. It stays constant. It's just going to be some number, some constant value k. It's the denominator that's getting arbitrarily large. It might be becoming a very large positive number or a very large negative number. Either case, the whole fraction turns into 0, right? So the general the general pattern that we want to fall into is that if we have some constant divided by a very, very, very large number, that's only getting larger. It's large already, and it's just growing bigger. The constant doesn't move. It could be 7, could be 2, doesn't matter, it just doesn't move. But the denominator is getting larger and larger and larger, then that fraction there is going to be getting closer and closer and closer to 0. Right? That's what that means. On the other hand, if we have k equal to some number, any real number, and we have x to the power of p like this, again, where p is some positive number, then the limit as x approaches negative infinity of that little product is going to be positive or negative infinity depending on the value of k and p. So depending on whether this is a positive or a negative and whether you're inputting negatives or positives. So it could vary a little bit, but these are going to be the cases where it grows toward positive or negative infinity. For example, we could look at the case where x grows toward positive infinity of, say, 3x to the 7th power. Here, the k equals to 3, and p equals to 7. And so as I plug in values that are getting larger and larger and larger, right, the inputs are growing toward infinity, a very large number raised to the power of 7 is just going to be an even larger number, and then multiplied by 3 makes it even larger. So this is going to be a case where it's growing toward positive infinity. Positive infinity. On the other hand, if I'm plugging in numbers that are growing toward negative infinity, so maybe I have the limit as x approaches negative infinity of 3x to the power of 7. So here the k is still equal to 3 and the p is equal to 7. But now as I plug in numbers that are very, very large and then raise them to the power of 7, they get even larger, and I preserve the negative sign so they become an even larger negative number. Times 3 is still going to give me a very large negative number, so this will be growing toward negative infinity. So you kind of have to think about it with these two cases, kind of decide whether it goes toward positive or negative infinity. If you can intuitively just kind of pay attention to whether you're plugging in large negative numbers or you're plugging in large positive numbers, and whether that results in a large positive or a large negative after you raise it to the power of p, and then decide whether the k is positive or negative to determine whether you're going to go toward positive or negative infinity. Okay? All right. How does that all help us? Let's look at this example here. So let p of x equal to 5 times x to the 3rd power minus 2x squared minus 3x plus 6. Find the limit of p of x as x approaches to infinity, as x approaches to negative infinity. Okay, so the limit as x approaches to infinity of 5x to the 3rd power minus 2x squared minus 3x plus 6. What I'm going to do is I'm going to do a little algebraic trick here where I'm going to factor out this term from the rest of it. So I'm going to say that this is the limit as x approaches to infinity of 5x to the 3rd power, parentheses, and now I want something so that this times the individual terms in here equal this. The first one's easy because that's just going to be a 1, minus, and now for the other ones I'm just going to employ this little trick. I want this times blank to be equal to that thing. So I'm just going to do this, x squared divided by 5x to the 3rd power. I know that when I distribute, the denominator and this term will cancel, giving me just that one. So it's just a little algebraic trick. I get this over 5x to the 3rd power plus 6 over 5x to the 3rd power. Okay, so next I want to reduce and simplify this a little bit. So this is equal to that. which is then equal to the limit as x approaches to infinity of 5x to the third power, 1 minus, and now these reduce, and so I'll end up with 2 divided by 5 over x, minus 3 over x squared, plus 6 divided by 5x to the third power. And now, using our theorem from above, I know that this is a constant. This is x to the power of 1. So let me rewrite that one more time, actually. Limit as x approaches to infinity, 5x to the third power, 1 minus, let's leave the 1/5 out of it. 1/5 times 2 over x, minus 3 over, oh, there's a 1/5 in there as well. 1/5. Okay, so this would be equal to the limit as x approaches to infinity of 5x to the third power times the limit as x approaches to infinity of this part, which is the 1 minus 1/5 2 over x minus 1/5 3 over x squared plus 1/5 6 over x to the third power. And we know that we can distribute that limit. And so this becomes the limit as x approaches to infinity of 5x to the third power times each of these. Now the limit as x approaches to 1, x approaches to infinity of the constant 1 is just going to be equal to 1 minus, and then we have 1/5 times this, the limit as x approaches to infinity of 2 over x. That's the case where, that's the same as the case where we have a k equal to 2 and there's this invisible 1 there. This is a p equal to 1. And so we know that this is going to grow towards 0. Good. Here we have a case where k equals to 3 from our theorem, and the p equals to 2. So again, this is going to be 0. I'll have a minus 1/5 times 0. And finally, same thing with this last one. This is the case where the k equals to a 6 and the p equals to 3. So again, this is just going to be 0. As x grows toward positive infinity, the denominator is going to grow toward positive infinity. And so 6 divided by a number that's getting infinitely large is going to go towards 0. So I'll end up with another term of plus 1/5 times 0. All of these become 0. And so I'll just get 1. So all of this begins to simplify, becomes the limit as x approaches to infinity of 5x to the third power times 1. So we can just ignore the times 1. And so now this is what's going to determine the behavior of our function. And we know that as x grows toward infinity, this is going to grow toward positive infinity, right? Very large numbers get plugged in. A very large number raised to the power of 3 is going to be an even larger number times 5, right? We're going to end up with a 5 times a large value, large positive number, raised to the power of 3. Well, that's going to be an even larger number that's also positive times 5, even larger. So we can tell from all of this that the answer is going to be positive infinity. Okay, so this analysis leads me to conclude that the limit as x approaches to infinity, positive infinity, of this function is going to be positive infinity. Good. The negative infinity is going to be very similar, right? We're going to do the same algebraic trick all throughout. But for the negative case, this is going to go toward negative infinity, 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 toward negative infinity. toward negative infinity. All of this stays the same, so that's still going to grow towards 0. This is just going to go toward negative infinity. So I'll have that as I plug in a very large negative number raised to the power of 3 remains negative, still becomes an even larger negative number, times 5 becomes an even larger negative number, which means that this will grow toward negative infinity. Okay, so let's put them together. I can conclude that the limit as x approaches to infinity of 5x to the third power minus 2x squared minus 3x plus 6 is going to be equal to infinity. And at the same time, the limit as x approaches to infinity of, as x approaches to negative infinity of 5x to the third power minus 2x squared minus 3x plus 6 is equal to negative infinity. The limit as x approaches to infinity of 5x cubed minus 2x squared minus 3x plus 6 grows toward infinity. And the limit as x approaches negative infinity of 5x cubed minus 2x squared minus 3x plus 6 grows toward negative infinity. Okay, limits of polynomials. So if we have a polynomial of this form, p of x equals to this, the standard form of a polynomial, where a sub n does not equal to 0. So we don't want the leading term to be 0 because otherwise it wouldn't be a polynomial of degree n. So we're just ignoring that case where the leading term is 0. And we want the n value to be greater than or equal to 1. So that we definitely have a polynomial that's of degree of at least 1. Then the polynomial has the following limits. The limit as x grows toward positive infinity of our polynomial is going to be determined by the front guy, the leading term behavior. The biggest exponent, right, and its coefficient in front are going to determine what happens to our graph at the infinities, at positive and negative infinity. Good. So in the short term, who knows what the graph looks like? It depends on all of the other terms and all the other constants. But as we grow toward infinity, as we let the input values get larger and larger and larger, it'll turn out that the leading term, the one with the largest degree, is the one that's going to determine the behavior of our polynomial. And that's because of this little thing here. Right? In other words, we started out with a polynomial. Here it is, a degree 3 polynomial. And then we can always do this kind of algebraic trick to factor out the first term, leaving something that looks like this. And then all these other terms are going to grow towards 0, leaving 1 times this term. So we can always manipulate our equation, our polynomial this way. And so this is going to be the term that determines what happens at the infinities. Okay, we call that leading term behavior. Notice that a polynomial of degree 0 is a constant. So if we have p of x equals to a naught, some constant, and its limit as x approaches positive or negative infinity is just going to be equal to that constant. So polynomial functions of degree 1 or greater never have horizontal asymptotes. They always grow toward positive or negative infinity. It's just going to be up to you to determine where it is heading, toward positive or negative infinity. So end behavior of a function. A pair of limit expressions of the form the limit as x approaches infinity of f of x equals to a, or the limit as x approaches negative infinity of f of x equals to b, where a and b are infinity or negative infinity or real numbers, describes the end behavior of a function. Right? So where is it going as x approaches infinity? Is it growing toward positive infinity, toward negative infinity? Is it growing towards some constant? Or is it bound between something, like a sine or a cosine? Okay. So the first of these two limits describes the right end behavior, and the second one describes the left end behavior. Right? So right end behavior because it's growing toward positive infinity, or left end behavior because it's growing toward negative infinity. So here's an example. Here we have another polynomial, right? We can do the same trickery as before, where I can factor out the 7x cubed, and then as we let x grow toward positive or negative infinity, the other terms get canceled out, right? In other words, I can do the same trick as before and rewrite it this way. I could say, let's factor out the 7x cubed, and I would end up with 1 minus 2x squared over 7x cubed plus 3x over 7x cubed minus 4 over 7x cubed. And then as x grows toward infinity, plus or minus infinity, either way, then all of these terms are going to grow towards 0, towards 0, towards 0, towards 0, meaning that as x grows, this will determine the final output of my function, whether it's going to go toward positive infinity or negative infinity. Good? So that's what we do here. We recognize that this is a polynomial, and then we want to know what happens at x grows, as x grows toward positive infinity or as x grows toward negative infinity. In those cases, we can ignore the other terms, just focus on the leading term, and the leading term will tell me what's going to happen. I know that if I input a large number and cube it, that's going to give me a very large positive number, right? If I input a large positive and cube it, I get a large positive number. Times 7 makes it even larger. I know that it's growing toward positive infinity. And as x grows toward negative infinity, again, it's the leading term that's going to determine the answer. So if I input a very large number into this, a very large negative number cubed becomes an even larger negative number. Times 7 grows toward negative infinity. So limits of rational functions and infinity and horizontal asymptotes of the rational function. So if we have a rational function of this form, which is one ugly polynomial in the numerator, another ugly polynomial in the denominator, this is where a sub m does not equal to 0. This is where b sub n does not equal to 0. So if we rewrite our polynomial in descending order, then the largest degree, starting with the largest degree, we just don't want that coefficient in front to be a 0. It could be anything else, right? Otherwise, it just kind of negates the whole thing. So if we have a situation like this, then the limit as x grows toward positive infinity of f of x is going to be equal to the limit as x grows toward positive infinity of the ratio of the leading terms of the polynomial in the numerator divided by the polynomial, the leading term of the denominator, the leading term of the polynomial in the denominator. Right? So we just care about these two in front. That will tell us the behavior. And that's true for positive infinity and negative infinity. And when we do that, we're going to get one of 3 possible cases that is based on the powers of n. So if m is smaller than n, if this degree is smaller than this degree, then it's going to turn out that both limits grow towards 0. Okay? And so the line y equals to 0 ends up being what we call a horizontal asymptote. Our function will head that way, will head towards 0. So let's see an example of this one. So if you have an ugly polynomial, but then you just focus on the first 2 terms, and we see those first 2 terms, and let's say that those first 2 terms are something like 3x to the 7th power divided by 9x to the 8th power. Here we see that the exponent, this is the exponent for the leading term in the numerator. So this is going to be playing the role of m. And this is playing the role of n. So if we have this case, m is smaller than n, then I know that the limit as x approaches to positive or negative infinity is going to grow towards 0. I know this whole thing will grow towards 0 as x grows toward positive or negative infinity. That's what this one is saying. So therefore, our output function is going to get infinitely close to 0. Good. On the other hand, what if they have the same values? If they have the exact same values, this would be a case like this, like maybe we have 3x to the 6th power divided by 5x to the 6th power. They have the same exponents. M and N are the same. That would be case number 2. Then the limit as x grows toward infinity, positive or negative infinity of our function, is going to be equal to the ratio of the two coefficients in front. So in this little example, it would mean that because they have the same powers, this will grow toward 3/5 as x grows toward positive or negative infinity. Right? That's what this is saying. And so our function gets infinitely close to this number. This number becomes a horizontal asymptote. Y equals to 3/5 in this case would be a horizontal asymptote. Our output values get infinitely close to that result. Okay. And finally, the last case is the case where the m is bigger than the n. So we might have a situation where we have 3x to the 5th power divided by 9x to the 3rd power, something like that. Here we have a case where the m is larger than the n. That would be this third case, right? And so then each limit will be infinity or negative infinity depending on the other values. I know that this will grow toward positive or negative infinity depending on the actual values of the coefficients and whether you're inputting values that are, as x grows toward positive or negative infinity. So it kind of depends on what kind of values you're inputting. You have to do a little bit more, have to think about it in that case. Okay, so only three scenarios will happen based on the leading term. Remember that all of these cases were just quick little examples where these are just the leading terms, these guys. Okay, there might be a much larger polynomial attached to the end of that, but we only care about the leading term of the new polynomial in the numerator and the leading term of the polynomial in the denominator. I know this is a lot, so let's look at this example. Find the horizontal asymptotes, if any, of the following functions. Okay, so what happens here? We have a polynomial in the numerator, a polynomial in the denominator. So all we're going to care about is the first two. Okay, so to consider these, we kind of go off to the side and think about what happens the limit as x approaches to infinity of 3x to the 4th power over 4x to the 3rd power. So this is a case where the m value is larger than the n value. The degree of the leading term in the numerator is larger than the one in the denominator. So this is the case where it's going to go to positive or negative infinity depending on what you are working with. So this is just going to reduce to the limit as x approaches to infinity of 3x over 4. And so as you plug in a very large number times 3 divided by 4, you're still going to have a very large number. So that just goes toward positive infinity. And then the limit as x approaches to negative infinity, you get 3x to the 4th power over 4x to the 3rd power, which becomes the limit as x approaches negative infinity of 3x over 4. So as I plug in a very large negative number times 3 divided by 4, it's still going to head toward a very large negative number. So there are no horizontal asymptotes here, right? So what we have discovered so far is that if I wanted to sketch the graph of this, here's x, here's f of x, I have no clue what happens for small values of x. If x is 0, if x is 2, if x is 9, I don't know. But I know that as I plug in very, very, very large numbers of x, as x grows toward positive infinity, I know that this graph is just going to go that way, toward infinity. And as I input values of x that grow toward negative infinity this way, then I know that my function, as x grows that way, I know that my function is going to go toward negative infinity, so it's going to have some sort of behavior this way. What happens in the middle, I don't know. Maybe it goes up and down and does weird things, I don't know. But I definitely know that this is how it behaves as x grows toward positive infinity or negative infinity. Okay, let's look at this other case. Now we have a different equation where now to examine what happens, let's say the limit as x approaches to infinity, and again we just take the leading terms into consideration, and this is a case where the m is smaller than the n, so this will reduce. We have the limit as x approaches infinity of 5 over 4x. So as x gets larger and larger and larger and larger, I know that this whole thing will grow towards 0. There will be a horizontal asymptote at the line y equals to 0, which is the x-axis. On the other hand, the limit as x approaches negative infinity of 5x to the third power over 4x to the fourth power is going to be equal to the limit as x approaches to negative infinity of 5 over 4x. And now if I plug in a negative, a very large negative number here, then the whole thing will become a very, very small negative number. So it's still approaching 0, it's just approaching it from the other direction. So again, this is a case where the m was smaller than the n. And so we have a horizontal asymptote at y equals to 0, or the x-axis. And finally, we have this case where now they both have the same degree. So the limit as x approaches to infinity of 7x to the third power divided by 3x to the third power, because they have the same degrees, is the case where m equals to 3 and also n equals to 3. And they kind of cancel, and so this becomes 7/3. Okay, so horizontal asymptote and exactly the same thing happens whether you have positive or negative infinity. So the limit as x approaches to negative infinity of 7x to the third power over 3x to the third power still going to be equal to 7/3. So you get the same answer from both sides. So what this is saying is that I know that if I wanted to do like a rough sketch of this graph, so here's the x-axis, here is the y-axis, there's going to be a horizontal asymptote at 7 divided by 3. So it'll be this line like this, and this is going to be y equals to 7/3, is this line like that. So I know that as I input very large numbers, my function is going to get infinitely close to this one. So it might approach it kind of like that, right, as x grows toward infinity, or it might approach it from the top down like that as x goes toward infinity, or it might do something where it kind of gets smaller like this and gets smaller and smaller and smaller and smaller and smaller. I don't know, but I know that it just gets infinitely close to that line in both directions. So again, as x grows toward negative infinity, I know that it will either maybe approach it that way, or maybe it'll approach it from the top down. Maybe it approaches it from the top down. Or maybe it'll dance around it for a while. Maybe it'll kind of come down and then up and then might do something like that. Okay, so it kind of helps us piece together what happens as the input values get infinitely large in the positive or negative direction. Okay, so here's an example. A newly released smartphone operating system gives users an update notice when they download a new app. So the percentage P of users that have installed the new update after T days is given by this function. So we input T number of days after the update is available, and then this function will tell us how many people have updated it. So if we let T equal to 0, for instance, we end up with 0 divided by 100, which is going to be 0. So on day 0, no one has updated anything. Okay, 1 day later, we'll have 1 squared times 100. Let me write some of those down. So P of 0 is going to be 100 times 0 squared all over something squared plus 100. When T equals to 0, we'll get P of 0 equals to 0 over 100, which is equal to 0. So on day 0, 0% of the population has updated the software. What about day 1? T equals to 1. Then we'll end up with P of blank equals to 100 blank squared all over blank squared plus 100. So we'll get a 1 there, a 1 there, a 1 there. So we end up with 100 divided by 101. So this ends up being with 0.99%. So this is a little less than 1%. That's what that means. So it's not 99%. It's a little less than 1%. Okay, so then if we plug in a 15, as you can see here, 100 times 15 squared divided by 15 squared plus 100, that whole thing gives you 69.2. If we plug in 25, we end up with 100 times 25 squared divided by 25 squared plus 100 equals to 86.2. So we can see that as the input values get larger and larger and larger, the output values here begin to grow. Are they going to grow out of control forever? No. Well, notice that if we think of this as a polynomial, this is a case where the degree of the leading term in the numerator, well, it's only one term, is a 2, and the degree of the leading term in the denominator is also a 2. This is the case where the m and the n are identical, so we can see that this is going to converge toward 100. Right? According to the theorem, the degrees of the numerator and denominator are equal. They both have a 2. This is a 2, this is a 2. And so, according to our theorem, this is going to converge toward the division of the two coefficients, which is 100 over 1. So I can tell that the limit as t goes to infinity of this function is going to grow toward 100%. Good. So as the number of days grow toward infinity, slowly but surely, eventually, the percentage of people that upload or update their phone will grow toward 100%. Okay, so here is our function, f of t equals to 100 t squared all over t squared plus 100, where t is the number of days since this update has become available. Of course, in this abstract world, the graph allows t to be negative, but we know that that doesn't make sense, so we just ignore it for the purposes of this situation. And so if we have a point on this graph, for instance, this is saying that at 0, no one has updated, and as we move on, say at let's go from 0 to 100. No, 0 to 100 by 1s. There. So now, as we let the number of days increase. At 13 days, approximately 62% have updated. As we keep growing, at 22 days, 82.89% have updated. And as we keep growing, we see we get closer and closer and closer and closer and closer to 100. So we'd say that we have a horizontal asymptote at y equals to 100. See, we get infinitely close to it, but never actually equal to 100. Even though it kind of looks like we would. See, like over here, it looks like we're kind of there. But in fact, if we zoom in, no, the other way. If we zoom in, eventually we see that there's always a little gap. It's never quite 100%. All right, let's take a look at the exercises in this section. Okay, problems 9 through 16 involve this graph, so hopefully it's clear enough based on the graph what's happening. Be careful with the limit. In some cases, it's asking you what happens as the limit grows toward infinity. Let me zoom in some more over here. So there's a distinction between asking you whether the limit is growing toward positive infinity, whether it's growing toward negative infinity. We're letting the input value grow toward positive infinity, or the input value grow toward negative infinity. So from this graph, we could see that it's heading that way. So that means it's heading toward positive infinity. From this graph, we could see that as x grows toward positive infinity, the output seems to be getting infinitely close to this horizontal asymptote there. Okay. On the other hand, from the graph, we could see what's happening as the input values get infinitely close to -2. We can see that our graph is growing toward positive infinity from one direction, and from the other direction, as x approaches -2 from the right-hand side, we can see from our picture that it's growing this way. Okay, so hopefully these are okay. You can just interpret them based on our graph here. Let's see, what else do you have? For these problems, an equation is given. Find the limit, use negative infinity, positive infinity when appropriate. So for example, if we look at number 18, we can see that we're interested in values really close to -3, and we're approaching it from the left-hand side. So if we plug in a -3, we get 9/0. So we know automatically that there will definitely be a vertical asymptote. Some number divided by 0 where the numerator is not 0. It's not 0/0, it's some number over 0. I know that there will be a vertical asymptote. I just need to determine if my function will go toward positive infinity or negative infinity. And to do that, we use a table, plug in values that are getting closer and closer and closer to -3, and you'll be able to determine whether it grows toward positive or negative infinity. Okay, so that's what we do for these guys. So you're going to use your calculator, plug this into your calculator, and then plug in values that get closer and closer and closer to this value, either from the left side or from the right side, to determine what's happening with your function. Right? Okay, so around -2, once again, we have a case of 0. -2 plus 2 is 0. And then the numerator will be -4 plus 2, so that'll just be -2. It's not 0. There will definitely be a vertical asymptote. Okay, so hopefully those kinds of questions are fine. Coming over here, the leading term of the polynomial, the limit as it approaches infinity, as it approaches negative infinity. Okay, so for example, for number 26, the leading term is going to be the degree, the largest degree. So that would be this negative x to the 6th power. That would be the leading term. So therefore, as we input values that are very large, as infinity goes toward, as the input values go toward positive infinity, this will determine what happens to our graph. So this will be the end behavior. So a very large positive number raised to the power of 6 will still be a very large positive number. Times -1 lets you go to negative infinity. So that's what will happen as we let the input values grow toward positive infinity. This will grow toward negative infinity. And then if we input a very large negative number and raise it to the power of 6, it will then become a very large positive number times -1 will still grow toward negative infinity. So for number 26, this is the leading term, negative x to the 6th power. And either way, when the limit as x approaches positive infinity or the limit as x approaches negative infinity will lead to positive infinity. Okay, so hopefully those are clear. Okay, 33 through 42, it says use negative infinity, positive infinity where appropriate to describe the behavior of each zero of the denominator. Identify. Okay, so we need to figure out when this rational function will be equal to 0. Some of them are easy, like here it'll be -3, here it'll be +4. If it's a little more complicated like these ones here, then you're going to have to factor it. And the values that result in a 0 in the denominator are potentially vertical asymptotes. We need the ones where there's a 0 in the denominator, but then when you evaluate it, the numerator is not 0. So, for example, here we end up with just -3, so -1 over 0 when x equals to -3. Here, if we put a 4, we end up with 4 divided by 0. So those are both cases where we'll definitely have a vertical asymptote. Here for this function when x equals to -3, and for this one when x equals to +4. Okay, for this one, there is no asymptote, right? Because there is no way to get a 0 in the denominator, so there's no vertical asymptote. For this one, if we factor it, we get 3 minus x, 3 plus x. So plus and -3 are two possible values for a vertical asymptote. And do the same for the others. On the other hand, be careful. Remember, there was a case where we were able to reduce it. So if it reduces, in other words, if we evaluate the function at a point and we end up with a 0 over 0, that's an indeterminate form, that might not be a vertical asymptote. Only when there is some number that's not 0 in the numerator and 0 in the denominator do we have a vertical asymptote. Keep going. Okay, so here, they give you a function, say like number 44. Here's a function, evaluated at 5, that should be easy. Evaluated at 10, that should be easy. For these guys, we have to think about our pattern, right? We had a theorem that stated that we want to look at the degree of the leading term of the numerator and the degree of the leading term of the denominator. In this case, that would be a 3 and a 3. They're the same. So our theorem indicated that we'll have a horizontal asymptote at -3 over 4. Graph it and confirm, then that's what you get. On the other hand, if we had something like this one, see the degree of the leading term of the numerator, polynomial in the numerator, is a 1. Here, the degree of the leading term of the polynomial in the denominator is a 3. 1 and 3. This is a case where this one is smaller than that one. And so our theorem indicated that this would have a horizontal asymptote at the x-axis, at y equals to 0. It'll grow towards 0 as we input larger and larger values. The denominator will grow much faster than the numerator, so therefore eventually we'll get a really ridiculously large number in the denominator relative to a much smaller value in the numerator, so the whole thing will grow towards 0. Find all horizontal and vertical asymptotes. Okay, so to find vertical asymptotes, we know we have to figure out when the denominator is going to be 0. There will be vertical asymptotes at all x values that result in a 0 in the denominator and a non-zero in the numerator. So for example, for number 52, x equals to 4 will be a vertical asymptote, right? Because that results in a 0 in the denominator, and 4 times 3 plus 2 is 14 in the numerator. So that'll be a vertical asymptote at x equals to 4. So we do the same for the others. Look for all the values, the input values that result in a 0 in the denominator and a non-zero in the numerator. To do that, we might have to do some factoring. To find horizontal asymptotes, we need to think about what happens as x grows toward infinity, and then look at the behavior of the leading terms. So the leading term here and the leading term here, they're both the same power. The degree of the leading term of the polynomial in the numerator and the degree of the leading term of the polynomial in the denominator, if they're the same, such as this one of our theorems indicated that this would have a horizontal asymptote equal to the division of the coefficients of the two. So in this case, 1 over 1. down over here would be a 2 over 2. Again, they have the same degree. Here they have the same degree, so it would be 2 over 1. Right? That's where the horizontal asymptotes exist. On the other hand, if we have a case where the degree of the leading term of the polynomial in the numerator, the degree is smaller than the degree of the leading term of the polynomial in the denominator, then that means that there will be, the whole thing will converge to 0. There'll be a horizontal asymptote at the line y equals to 0 or the x-axis. That's the case for example, number 56. We have a 1 there and a 2 there. This whole thing will grow towards 0. That's also the case for number 60. We have a 1 there and a 2 there. This whole thing will grow towards 0 as x goes toward infinity. Right? So a horizontal asymptote there. On the other hand, if we have a case where the degree of the numerator is higher than the leading term of the polynomial in the denominator, then we have something that will grow toward infinity. Positive or negative infinity, we'll have to figure it out, but it does not have a horizontal asymptote. So that is the case, for example, on number 55. This degree is higher than that degree. The 3 is bigger than the 2. So I know that this will not have a horizontal asymptote. It will either grow toward positive infinity or negative infinity. Kind of figure that out depending on what you input. Hopefully that's enough of a hint to help you with that. Give a limit expression that describes the end behavior. Okay, so hopefully you're equipped for that. Okay, so that should be enough hints to be able to do this homework. Okay, so attempt the homework and let me know if you have any problems, questions, or issues.